Thank you very much, Nina, for the introduction, and I would like to thank the organizers for first of all, for the invitations, and second, for the very nice organization of the conference and the conference program, because most of the concepts I'm going to introduce have been already mentioned at this conference, like skyrmions, also neutron scattering, and even dipolar interactions. So indeed, now I work at Basis 2 Synchrotron that belongs to Helmholtz Zentrum Berlin. And I mainly work on small angle X-ray scattering investigations of long periodic magnetic structures in non-centrosymmetric magnetic materials, also hosting skyrmion textures. We've seen these images already a couple of times at this conference. I just want to remind that in magnetic materials, many kind of topological textures can be stabilized, in addition to skyrmions that host the topological charge of -1. Some materials have been shown to host antiskyrmion spin texture that host an opposite topological charge, but also bimerons with topological charge of 1/2 can be stabilized, skyrmion molecules, high-order skyrmions, ferromagnetic skyrmions, antiferromagnetic skyrmions. In bulk materials, often skyrmions actually occur in the form of three-dimensional skyrmion tubes, and even Hedgecock, anti-Hedgecock lattices have been observed in some of the B20 magnets. And if you go further in the 3D world, then other higher order topological spin textures can be stabilized, such as various Hopfions. Yeah, and some of these materials that are highlighted by these boxes have been already observed in bulk forms of magnetic materials, but some are still scarce. So, and my main interest is to investigate the magnetic interaction that can potentially lead to any kind of topological and non-trivial spin orders in centrosymmetric and non-centrosymmetric magnetic materials. Just a brief reminder why it's actually exciting to have topological spin textures is the main motivation is that due to the topological spin texture, so-called Berry phase is generated that results in bending electron trajectory, bending trajectory of electrons that are passing through the topological spin textures, and also the same electrons that are pushing skyrmions that make them basically move, and this can be used in racetrack kind of devices. And this Berry curvature also can be observed in magnetic transport measurements that manifest in so-called topological Hall effect, where in addition to the normal Hall resistivity, which is linear in magnetic field, and anomalous term, which is linear in magnetization, you also have another term that corresponds to the non-trivial topological magnetic structure. This term can be ascribed as topological Hall effect. So, and you can see a very bright example in manganese silicide is when you apply magnetic field and go into the skyrmion pocket phase, then you have a large enhancement of the Hall resistivity here. And if you calculate it into effective magnetic field, it is of an order of tens of Teslas, and which is generated by only applying a few hundred milliteslas in these materials. And this so-called emergent field is one of the brightest manifestations of topological spin orders, at least in metallic compounds. And there are numerous proposals for applications of magnetic skyrmions, starting from racetrack memories that I mentioned already to high-frequency oscillators and unconventional computing, like reservoir computing, that has been already introduced perfectly yesterday. And I'm not going to talk about these, but I would rather talk about the underlying magnetic interactions and how we investigate them. My main tool now is using polarized X-rays to study long periodic magnetic orders, and the contrast mechanism of generating magnetically scattered photons is the following. If we have 2 pi core shells and spin polarized 3D band with photons carrying opposite orbital moments, orbital momentums, meaning left or right circularly polarized. We can selectively excite these 3D to 2 pi transitions. And the absorption coefficient and refraction coefficient would depend on the spin moment parallel or anti-parallel to the circular polarization plane. So that creates the unbalanced absorption and or fluorescence in the X-ray spectrum. For example, if you have a magnetized iron with a moment parallel to the perpendicular to the polarization plane of the circularly polarized light, you have a difference between left and right circular polarizations. And if you can focus the X-ray beam and scan your piece of iron with left and right circularly polarized X-rays, you will see the magnetically dependent contrast. That's because the absorption coefficient for left and right polarizations will be different, and if you take a difference or divide one to each other, you can even enhance this magnetic contrast and see the magnetic domains. So this absorption coefficient basically is exponential and depends on the on your material, on its magnetization, and you also have the thickness in this exponent, which is important because here we are talking about so-called soft X-ray regime with photons lying in the region of a few hundred of electron volts, which corresponds to a few nanometers in the real space. So basically, if you have the contrast mechanism, you can then implement any kind of optical technique like microscopy and diffraction, small angle scattering, and so on. So my main tool is indeed scattering. So as I mentioned already, we have photons with wavelengths from a few hundreds to 1 kilo electron volt that correspond to absorption ages of transition metal elements. That corresponds to wavelength from 10 to 30 angstrom roughly. And because of these relatively low energies of photons, we are extremely sensitive to the thickness of the specimen, and we can probe only a few hundred nanometers on the surface because for thicker samples, the signal will be just absorbed. So this is a trade-off between the intensity of magnetic scattering, which is, depends quadratically on magnetization, and the exponential decay of the absorption. So the optimal thickness of the sample you can try to measure is of from few tenths of nanometers to a few hundreds of nanometers. And the important thing to have in mind is that in addition to magnetic scattering, you still have the Compton scattering and interference between them. Compton scattering has a magnitude of, it's about 2 or 3 orders of magnitude stronger than the magnetic one. So that would be difficult to study some ferromagnetic materials where you would have an overlap between charge and magnetic scattering, just because the magnetic scattering intensity is too small. But if you have the spatial separation in the reciprocal space of your magnetic modulation vector and your charge modulation vector, like if you have an antiferromagnetic material or a helimagnetic material that gives you incommensurate magnetic satellites, like the ones you can observe in the copper selenide, as was discussed yesterday. You can rather easily separate charge and magnetic scattering and investigate your magnetic structure directly. And yesterday, Dennis nicely introduced a small angle neutron scattering technique. So just briefly remind what it is. So if you have long periodic magnetic or any other kind of structures, you apply the Bragg's law for a small angle scattering regime. And if you find out if at wavelengths of a few angstroms that you typically have in neutron instruments, if you want to investigate some periodic structure of a characteristic wavelength of tens of nanometers, you really have to go to small angles. And that means that with divergent neutron beams, you really have to build large instruments. So typical small angle neutron scattering instrument, it has like 20 meters of the collimation length for neutrons and another 20 meters of sample detector distance just to resolve these small angles. Additionally, in neutrons, you have really physically big detectors because 2D detectors actually consist of macroscopic helium glass tubes filled with helium-free gas. And the typical pixel size is actually 1 by 1 centimeter or so. And in contrast, what we can do in X-rays, we have, first of all, wavelengths that are a few times longer. So that already provides us higher resolution. Also, the wavelength distribution is much more narrow. The X-ray beams can be generated with quite low divergency. So we don't need large collimation lengths. And also the pixel size of X-ray detectors, this is typical CCD as you have in the smartphone cameras or photo cameras. The pixel size is just a few tenths of micrometers. So that generates a really high reciprocal space resolution in X-ray experiments, and you don't really need to build that large machines. So these are small angle X-ray scattering chamber at Photon Factory. It occupies the space of 2 by 2 by 2 meters or so. On the other hand, because of these long wavelengths, you have large absorption of soft X-rays, so you have to really make them thin. And how it can be done? So in case of single crystals, you can deposit them on substrates that are transparent for X-ray beam. So for this, silicon nitride is typically used because it's mechanically robust and also quite transparent in soft X-ray regime. So 50 nanometer thick silicon nitride membrane would give you almost 100% transmission. And you can easily buy them from commercial companies. And then the next step, we also coat them with a 1 micrometer layer of gold. I will explain why do we do that in a minute. And on the sample side, we have to thin down our bulk single crystals. For this, we use focused ion beam technique for nanostructuring. So first of all, as I said, we coat the membranes with a layer of gold. And then we mill, by using focused ion beam, we mill a circular or rectangular or square aperture in the layer of gold. Why do we do that? Is because we want to study very small samples, but we have the beams of a size of, let's say, 100 by 50 micrometers. And if we have samples smaller than the beam size, then we'll also have some strong background from the tails of the direct beam. We want to avoid that, so we use this kind of aperture. Then we take our single crystal material, we make trenches with the gallium ion beam. We pick it up by using micromanipulator, put it on a copper grid. Then we further use weaker gallium beam to thin it down to 100 nanometer or so. We again pick it up using the micromanipulator and attach to the aperture on the silicon nitride membrane by depositing some platinum gas or tungsten, carbon, or whatever you have in the FIB setup. So and this is the final image of the device. This is a thin piece of single crystal chiral magnet and placed on the aperture with a size of, say, 10 micrometer. So then turning to the instrument side, so now I work at BESI-2 Synchrotron. It's located in Adlershof in Berlin and belongs to Helmholtz Zentrum Berlin. So it's rather old facility. It has been commissioned in 1998, and it's facing a minor upgrade soon. It has the circumference of 240 meters that allows to accelerate electrons inside the ring to the energy of 1.7 gigaelectron volts with a nominal current of 300 milliamps. And these electrons, they generate synchrotron radiation with energies from 1 to 150 kiloelectron volts with a maximum flux at around 500 electron volts. So it's rather soft X-ray dedicated facility. And yeah, it's famous for its beam stability and time-resolved applications. And the instrument I'm working at, in particular, is located at PM2 beamline. The end station is called VECMAG, meaning vector field magnet, obviously. So the beamline is the dipole beamline, located at the bending magnet. So it provides X-rays in the energy range from 20 to 1.6 kiloelectron volt. We have about 5 to the 9 photons per second with the 77% circularly polarized. We can tune the beam size from few tens by tens micrometers to about 1 by 1 millimeter. So we have about 30% of beam time dedicated for our experiments and machine commissioning, and about 70% of beam time for user experiments, so anyone can actually apply and come for the measurement. So important features of the setup is that it's quite optimized for small angle X-ray scattering in transmission geometry, because we have a large CCD detector, and also we can go to low temperatures and high magnetic fields, and most importantly, we can also apply vector magnetic field up to 1 Tesla in any direction. Yeah, and I'm giving you a first example. This is the high-resolution small-angle scattering that allows us to capture some weak effects in cubic chiral helimagnets. So if you consider a cubic chiral magnet with Jalshinsky-Marie interaction, so it has a helical ground state, and if you apply the magnetic field, it turns the propagation vector of the spiral along the field direction. Here, we are not considering skyrmions yet. And in the ground state, the helical propagation vector is given by the combination of the magnetocrystalline cubic anisotropy and so-called anisotropic exchange interaction. So if you solve this problem that has been done in 80s by Buck and Jensen, so-called Buck and Jensen model, so you can result in the wave vector of the spiral given by the ratio, mainly by the ratio between D and J, so between the Jalshinsky-Marie and exchange interaction, but you also have a high order correction due to the anisotropic exchange interaction, which is usually considered weak, of an order of few percent of D over J. But it's actually important for defining the propagation vector of the spiral in your system. So for negative exchange anisotropy constant, the spiral tends to propagate along 1 by 1 direction, but for positive ones, it propagates along the cube axis. And it has been neglected actually for years until recently, because we were able to quantify this anisotropic exchange. Basically, with the high-resolution X-ray scattering, we could measure these weak corrections to the spiral propagation vector by applying X-ray scattering in a vector magnetic field. So we did it first for iron germanium. We found just a few percent correction, so it's really weak interaction. But why it might be actually important is because in copper selenide, which is much more anisotropic material, the phase diagram is richer, and when you apply magnetic field along the cubic axis, in addition to the conventional helical, conical, and skyrmion lattice state at high temperature, at low temperature you also have tilting of the conical spiral up to 30 degrees away from the magnetic field, and also low temperature skyrmion phase is somehow stabilized. And Andrei Leonov from Hiroshima University came up with a theory that these low temperature phases can be explained by competing magnetocrystalline and exchange anisotropies. And that's why it's important to quantify this interaction. And that's the method I presented is the only one I know that allows to do that. So we nanofabricated copper selenide crystal. We verified the helical ground state and conical state that follows the magnetic field. We also take one image in the skyrmion phase just to confirm it. And then what we can do is we apply the magnetic field in 001 plane here and follow the propagation vector of the conical state. So here we rotate, we rotate the magnetic field in this plane, and we, at each rotation angle, we have the two conical peaks following the magnetic field direction. And then if you map out this movie on the same image, I'm not sure if you can see it well, is this structure definitely deviates from a circle. And if it was on a circle, that would mean that basically the propagation vector is isotropic within this plane. But it definitely has some humps and dips. And we found that these humps and dips, they actually correspond to the principal crystallographic direction in this crystal. So the K vector has maximum for 110 direction and minimum for 100 equivalent. And we directly apply the theory that we presented before, and we have only one fitting parameter, and we can quantify this anisotropic exchange parameter. So, and we find also that it's temperature dependent first, so it really appears at low temperature and goes away at high temperature. Okay, here we still have some uniaxial anisotropy induced actually by the strain applied on our crystal. And yeah, by fitting this equation, we can easily obtain the temperature dependence of anisotropic exchange, and we really see that it's enhanced towards lower temperatures, and therefore it's likely supporting the theory of Andrei Leonev about the competition between the exchange anisotropy and cubic anisotropy, because we see the exchange anisotropy really gets quite large at low temperatures. And the next example is another system. It's a so-called Antiskyrmion host. This is the system from Max Planck Institute in Dresden. And in contrast to cubic chiral magnets, it's tetragonal. And for the symmetry class, in principle, if you have the helical ground state along the square axis within the tetragonal plane, you would have a helical ground state with opposite chiralities. And if you apply magnetic field, you will have anti-skyrmion phase, which can be viewed as a hybrid structure between two block-type helices and two Neal-type cycloids. And we have found that if we apply the in-plane magnetic field, we actually see that the spiral propagation vector tilts away from the direction of magnetic field. And it's already surprising that it doesn't follow the field as the helical structure is supposed to, but it behaves rather like a cycloid. And also there's a temperature evolution of this tilting behavior. And this is very strange, and this is not actually supported by the symmetry of the system that defines clearly helical and cycloidal states here. And if we do the full vector field analysis, we again see that we can fully control the propagation vector of the spiral within the tetragonal plane, and it's definitely not something that the symmetry of the system would allow us to do. So we can conclude that the dipolar interactions are actually dominating the spiral system in this material instead of the Zolshinsky-Marie interaction. And the most surprising thing is we have found that if you stabilize the single domain structure with the propagation vector along to say 100, and then you apply the magnetic field along the Q vector, so this spiral structure wants to reorient in orthogonally to it, it actually goes, the reorientation process actually goes via some triple Q magnetic structure showing this hexagonal spot lattice. That means our guess, we don't have a proper theory for this, is these two helical states that in principle should have orthogonal chirality. And if the system wants to change the chirality, it goes somehow via a non-chiral state, which can be triple Q anti-skyrmion state or some kind of skyrmion state. We would be happy to get some theory insights for. Yeah, and just a few conclusions is I hope I convinced you that resonant small angle scattering is a very powerful tool for this kind of studies of non-centrosymmetric or long materials and long periodic magnetic structures. We have naturally provided element selectivity, quite flexible sample environment, and as soon as you can work under high vacuum conditions, where we can study very small samples. So we don't need large single crystals like neutron people do. But on the other hand, we were limited to study surfaces or very thin magnetic systems, and it can be used as a complementary tool for neutron scattering and electron microscopy. And as a result, we have quantified small anisotropic exchange parameters in several materials already. and we add some knowledge for D2D systems hosting Antiskyrmions. Yeah, for more details on theory and also experiments, yeah, you could refer to these two recent papers. With that, I thank everyone who contributed to this research, and again thank the organizers and you very much for your attention.